So where does the problem of microplastics come from? So there are about 8 million tons of plastic wastes which are deposited into the oceans annually. These plastics break down into smaller particles of less than 5 millimeters in size, and then they're then classified as microplastics. Once these are in the ocean, you can imagine they can be ingested by aquatic life, and then any other organism which consumes fish, which is aquatic life, which is part of the food chain, may be affected. So there are a number of studies going on how microplastics, might affect organisms. And so we found that the best way to actually combat this problem is to assist with microplastic research efforts so that as more data is backed up and analyzed, the government actually has more solid data to reference as they make better and more effective policies to combat the problem. So in the research process, one of the main things researchers do is count microplastics and also identify them. So while they're counting them, it's typically like a manual process where people have to maybe make educated guesses, estimate, or they have to individually count particles. So additionally, when they're identifying them, they have to use maybe spectroscopy, which may not always be accessible to many laboratories. Some existing solutions are gravimetric analysis, which is from the picture, you can see that it's like they would take a weight of a sample and then compare it to maybe the standard weight of one microplastic, an average weight, and then find like what the number of microplastics in their sample could be. The now red staining visual analysis method involves using a red dye. This one is particularly useful in that it will distinguish between the microplastics and organic material, but you would actually still have to visually, like individually count like which microplastics have been dyed and then record them. With gas chromatography, the microplastics are heated up, and then once they're in gaseous form, they're illuminated. Then that light is used for viewing the spectra and then identifying and counting the microplastics. With spectroscopy, it's using infrared for spectroscopy. In the FTIR machine, we're going to mention it later on as well, which is quite an expensive tool, but it's also accurate and it's used by labs with access to it. So we talked to a number of stakeholders to really gain more insights on this problem. So we did talk to stakeholders, and we found that they would be counting each plastic individually. So from their given sample, when they're doing post-processing, they're counting individually. Likewise, this environmental toxicologist was also individually picking plastics from sieves. So sieves are used to, because they filter out the plastics. And so he would individually be doing that. So again, a manual process that takes time.
From speaking to researchers, we found that there were 4 main steps in counting microplastics in a sample. The first step is extraction, where a researcher collects microplastic samples out of the water. This is normally done using either Newston nets or with deep water pumps, or by just bottling water straight out of whatever body of water they're researching at. Then the microplastic sample is processed. The samples are cleaned through oxidative agents that removes organic material from the water sample. And then the sample is enumerated, which is normally done through visual analysis using an optical microscope. However, it can be aided by more expensive equipment if needed. And then finally, microplastic samples are chemically identified to ensure that the things that were enumerated are actually microplastics and to determine what type of plastic they are. Spectrometry, especially FTIR, Raman, and gas chromatography along with mass spectrometry are normally used as the main chemical identification methods. The MIQS system falls in at the enumeration step, where we will automatically count microplastics in a clean particle sample. We will sort the particles into size groups as well as sort plastics out of bulk particulate. We have several quantified characteristics that were taken over from stakeholder conversations. First, we realized that 75% of stakeholders focused on particles that were 100 microns or greater. So we plan to analyze plastics from 5 millimeters down to 100 microns, where 5 millimeters is the maximum for microplastics by definition. We also realized that the shortest stakeholder processing time we received was 24 hours. Some stakeholders even mentioned that they would be willing to wait a week. So we decided that we would process a sample within 24 hours or less. We realized that 75% of stakeholders had FTIR machines, and from those stakeholders, we learned that FTIR is about 80% accurate in the identification of plastics. We learned this from some of their papers along with some of their communication with us. We also learned that in visual analysis, fluorescent microscopes are often used in order to identify plastics that are dyed with fluorescent dye. And those microscopes are normally around $5,000. So we decided our cost should be less than $5,000. And stakeholders desired an average of about 1.5 hours as their max interaction time with the device, with a mean of 2 hours. So we require that our device should have less than an hour's interaction time. We look at the niche of mixed system based on those quantified characteristics, and we realize that the different applications that are already solutions in this space are microscopy and chromatography, the visual analysis, and the gravimetric analysis as mentioned earlier, where the microscopies and spectrometries, chromatographies, those types of systems are all very accurate. However, they have low throughput because they normally require a manual process to take plastic samples from the visual analysis into those microscopy systems. The visual analysis itself is low throughput as well because it is a manual process, and it's also inaccurate because it requires a researcher to identify plastics by only vision, by only sight. And gravimetric analysis is high throughput, but it's very inaccurate because a researcher will only be able to mass a bulk amount of microplastics out of a sample, but they won't necessarily individually count how many microplastics make up that bulk mass. So the MIQS system hopes to be both accurate and have a high throughput given the quantities that we mentioned earlier as our system characteristics. We also look at the niche the MIQS system has in comparison of expense to throughput, and we realize that while the systems that encompass microscopy, spectrometry are very expensive and low throughput because they are manual, and the microplastic visual analysis is low throughput and inexpensive because most labs already have or can purchase a optical microscope that is capable of working with these samples. The MIQS system actually shares this space with the gravimetric analysis in that they're both high throughput and inexpensive. We look now to a system level down selection where we compare gravimetric analysis, Nile red microscopy, which is the microscopy using Nile red as a dye, as a fluorescent dye, computer vision, and microfluidics. And we realize that computer vision and microfluidics are both able to reach the system characteristics that we had mentioned in previous slides. So while we move forward in this presentation with microfluidics, we do plan to go back and rescale our project to see if computer vision would fit it better. We then look to microfluidics and down select among the many different forms of microfluidic systems that there are. After looking at many different methods of microfluidic analysis, as you see here, we finally down selected to sedimentation and resistive pulse sensing as a joint process. We decided to down select based on sedimentation, as it is a passive system that would allow us to determine the microplastics compared to other particulate, and the resistive pulse sensing, as it would allow us to implement simple electronics to determine the size of the particle and verify with the sedimentation step. Our final idea, based on all of those down selections, is a system as is shown here, where you initially have the inlet syringe reservoir, which feeds into a peristaltic pump. The pump is connected to the microfluidic chip, which is sandwiched between two PCBs, where the electrodes would be able to interface with the computer. You also have a USB connection that would allow these electrodes to feed their information into the microcontroller. You have the power for the PCB, which should be a separate power from the pump. And then the microfluidic chip leads into the outlet syringe reservoir. The general process of user interaction with this system should be that a user cleans a microplastic sample, evaporates water from the cleaned sample, and puts the microplastics into the input chamber. Then the input chamber will be filled with saline solution, and the pump will be plugged in to the inlet reservoir, while the microfluidic chip will be plugged into the output reservoir. And then the device will be turned on as things start pumping from the inlet all the way to the microfluidic chip and out.
In this section, I'm going to be talking about the microfluidic chip physics. So the microfluidic chip is going to be segmented into the sorting and the counting aspect. In the sorting aspect, we're going to be using sedimentation sorting, and it works in the sense that it's going to sort the microplastics by size and density. What you do is you insert the particle suspension in one inlet, and in another inlet, the fluid without the particles in it. You pinch, i.e. you reduce the diameter of the channel. And then once you increase this channel diameter afterwards, we see that particles are going to rise based on their density and their size. So you tend to get the smallest size, lowest densities rising higher than the largest size, larger density. So this is just a good way for us to sort of sort. And as you can tell, we see like we have different densities for plastics, plant matter as well. So this is also another good way for us to ensure that we are getting rid of some of the other particles that may not be microplastics within the sample. Getting into the resistive counting. The idea behind this is that as you pass particles through a pore or a channel, the particles should displace the fluid. And because of that, you should be able to detect a change in resistance. So with this change in resistance, you'll be able to measure the voltage, which will then help you identify the size of the particle, because the larger the size, the larger the change in resistance you will observe. When looking into what this represents mathematically, using the equation from the last slide, we can see that for a size length of 6 centimeters and a diameter of 6 millimeters. The diameter is to accommodate the largest particle size we have of 5 millimeters. We see that the resistance increases and the minimum target diameter that we have is 2.9 millimeters, and the smallest that we could detect is 1.5 millimeters. And the same could sort of be taken into consideration when you're rescaling the particle size and the particle diameter, particularly for the channel. We can see that once we reduce the channel diameter, we're able to detect the particle sizes that in the larger diameter we were not able to do so.
So now I'm going to talk about the circuit design. In this circuit design, we can see a setup where we have our electrodes, which is where the plastics will pass through and then they'll cause a change in resistance. So resistance is proportional to voltage. So we'll be measuring that change in voltage. And the way we'll be doing that is through a voltage divider circuit. So what do we measure here? We measure Vx. That voltage is amplified through the two amplifiers. The first one does the amplification that we want so that it's in the volt range, unit range. And then the second amplifier is just to turn the voltage to negative because inverting amplifiers have a negative gain. So once they're at the microprocessor, then we can back calculate the change in resistance, which tells us the size of the particle. And after that change of resistance is recorded, we can also increment the count. So as this particle is passing through, we're incrementing and so getting the number of plastics passing through the electrodes. So one thing about this is the particle voltage changes in the millivolts range, which is actually sufficiently large compared to the noise range of microvolts, which is mentioned in papers. But we do know that we could expect higher noise levels. So we are consulting people in the electrical engineering department who will help us with small signal measurements. But we do know that, to make sure that noise doesn't affect as much, we need to make sure that the voltage we're measuring is orders of magnitude larger. And the way we can do this is increasing the channel size. Now we go to microcontroller down selection, and we did decide to go with the Raspberry Pi because it had the highest operating frequency, and this was important to our designers who wanted to make it fast enough. I'll leave it to Tony to talk about fabrication.
Looking at fabrication, there are three main items that have big fabrication processes that need to be considered. The first is the microfluidic chip, which will be primarily done through SLA 3D printing. The fabrication process here is that a print job will be sent to the SLA printer. The print will be washed with alcohol and distilled water in order to clear the channels. Then a needle inlet will be press fit into the channel inlets in order to allow the water to actually flow from the microfluidic chip into a pump. And if needed, the inlets will be fixed to the channel openings using epoxy. In these procedures, the use of the AdLab will be required for our final prints. However, in intermediate test print jobs for the microfluidic chip, we will use a personal SLA printer, the Anycubic Photon-S. We also need to consider the electrode patterning part of the fabrication process, where we have two main approaches to this. We can send our designs for an electrode out to a professional patterning company to print for us. That would only need us to design an electrode on SolidWorks, create a DWG file, and send these files over to a professional patterning group. Alternatively, we can also print the image that we create onto vellum paper, stick copper tape to the back of this vellum sheet, score the electrode out of the paper copper combination, and insert this paper electrode into the slots of the microfluidic chip to also have their functionality. We finally also require some fabrication to be done on the syringe reservoir, where a syringe normally is relatively high tolerance. It is time consuming to machine something that high tolerance over and over again, especially if we go through several iterations. So instead, we can purchase a syringe and do some machining on the plunger to allow the application that we wanted. So what we would do is purchase the metal syringe, remove the rubber plunger, drill and tap through the plunger, and drill and tap externally a separate rod that would allow us to have an input into the syringe reservoir. Then we can screw this separate rod back into the plunger so that when we are actually conducting an experiment, there is no contamination from external microplastics into our sample. Now we'll move on to validation step. Now we will move on to the validation step.
In this section, I'm going to be talking about all the tests that we're going to do to ensure that the system and all the subsystems work as intended. So the first one that I'm going to be looking at is the sedimentation subsystem. So the way it's set up is we're going to have the sample input range and the driving input range be injected at the same time. We're going to have the pumps give us a constant flow rate as they enter into the microfluidic chip. And then we're going to have the particles sort of separate as intended. So to give a more specific example into how this is going to be done, we intend to have four output channels for four categories: smaller size, low density; smaller size, high density; larger size, low density; larger size, high density. And as we talked, the idea is to ensure that the system is able to sort this accurately. So we're going to be putting for 20 microplastics into the whole system, hoping to get 5 microplastics in each channel correctly. Once this is completed, we will repeat the experiment to ensure that we are able to get results for even smaller sizes, even different variable sizes with more output channels. So for the pumping subsystem, we're gonna have the syringe in a stand, and then we're gonna connect it to the pump, have the water go through the microfluidic chip and go out into a plastic cup. So the way this system is going to work is that the channels for the microfluidic chip initially are going to be 5 millimeters channel sizes. And then we're going to put a known amount of fluid in the pump. Through the pump, we're going to put it in the syringe, pump it at 2 milliliters per hour. Have this pump run for 20 minutes. The idea being to observe that we can get constant flow rates, but also flowing it through the chips to ensure that the pump does not rupture the microfluidic chip. And then once this is done, we will repeat the experiment for smaller channel sizes. Looking at the counting, we're gonna have a channel input where we're going to be inputting the saline and the microplastics. We're gonna have the injecting pins for the current, and then we're gonna have the electrodes that are going to be we're using to measure the resistance. So the way this is going to work is we're initially going to inject the saline alone to ensure that we get the resistance without any microplastics or any particles in there. And then we're going to introduce a microplastic, 5 millimeter size. And then we're going to measure the resistance that we're going to get for that. And then we're going to repeat the experiment for smaller microplastic sizes, smaller microplastic microfluidic chip channels. And then ideally towards the end, we want to be able to have a mixture of microplastics in different sizes to see if we can accurately get the resistances. By putting in known sizes, we know what resistances and changes we are expecting and what sizes that should correspond to. So that's what we're initially going to be looking at. Considering the timeline for the project, mainly up until the end of the semester, we're going to be considering a lot of the down selection between microfluidics and computer vision and zoning in on that. The January is going to be based a lot more on CAD designing and building the circuit, with February being for testing, mainly for the microfluidic chip and circuit prototype. And then for testing, we're going to be doing for the pump and the reservoir in March, beginning of March. And then once all of these subcomponents have been individually tested, we're going to assemble and test the subsystem before we give it to stakeholders to test and give us more feedback, all which should hopefully be well in time to submit the report and for design day. So a summary, we've seen inefficiencies and lack of standards and microplastic research. Right now, our plan is to give the stakeholders a microfluidic device that can count and sort microplastics. The end goal is to be able to inform policies. But for now, with the system being able to count and sort, we want to then be able to enter into the section as well, where with this information, the researchers and stakeholders are able to identify the microplastics. Once this is done, we'll have more information on how dire the situation is all over the world, and researchers could use this to quickly get results. Um, for our fourth deliverables, our main thing is to ensure that we down select properly between the microfluidic and computer vision. We want to thank all our advisors, mainly Paolo Ratia, who's our faculty advisor, and all our technical advisors as well for all the input they've given us. Thank you.